Okay, let's come to order here. So, welcome to the session on earthquakes in the central and eastern U.S., and we need to get started here. So, Bob Herman from St. Louis University is our first speaker, and we will turn the podium over to him right now.
Great, thank you. I think the lead-off is what I'm not going to talk about, and having been involved with Eastern U.S. seismicity for a while, I'm not going to talk about why do we have earthquakes. I'm not going to talk where they're going to occur in the future. I'm not going to talk about recurrence, and I'm not going to talk about MX. What I want to review is some of the successes we've had in the Eastern U.S. recently, some of the challenges, and perhaps, and then finally, to offer some suggestions for further discussion as to where we go in the future. Thank you, Randy. Successes are earthquake monitoring and source parameter determination. Next, please. This is a slide showing what's available in the public continuous wave buffer of NEIC. It represents all the broadband stations as of last week. They are those sponsored by run by the United States Geological Survey, sponsored by the USGS as part of the Advanced National Seismic System, and also some of the stations of a proposed transfer of TA stations to the USGS as the Transportable array winds to its end in the continental North America. And just from that particular slide, one could say that monitoring is fairly uniform in the eastern U.S. So monitoring looks good. Next one, Randy. What else can we do? We can determine source parameters of larger earthquakes. The red beach balls up in the top left indicate the earthquakes, moment magnitudes greater than 3.5 in the continental U.S. and southeastern Canada that have occurred this year. The bottom right is just a way of summarizing the feature of the earthquakes. The colors indicate type of faulting. Blue would be thrust, green a strike slip, and red would be normal faulting. The little rectangles are oriented in the direction of maximum compressive stress. Interesting patterns there that might be useful for trying to understand why we have earthquakes. Next one, Randy. Successes. August 2010, 2011, there were some small earthquakes that occurred in eastern Arkansas. Steve Horton of the University of Memphis, SIRI, put out portable instruments. Additional instruments were provided by NEIC, which happen to have real-time telemetry. And because of access to the continuous wave buffer, because of Arkansas Geological Survey Network, it was possible to obtain a lot of waveform-based moment tensors for events with moment magnitudes greater than 3.5. Those are the colored beach balls. They don't superimpose. The patterns don't superimpose because the beach balls use the initial location, whereas the seismicity pattern used the local network data. Next one. Sort of the biggest success as far as monitoring and the most significant earthquake in the East, at least since 1886, was the Virginia earthquake on August 23, 2011. This is just a figure showing some of the locations of aftershocks, color-coded by depth. If we go to the next slide, looking on the BB prime profile, a very definitive dipping pattern of seismicity, and so for perhaps one of the few times for eastern U.S. seismicity, there may be a chance of identifying the fault plane. Next slide, please. The reason this was so successful is that immediately after the earthquake, because of the significance of the earthquake, there was a lot of cooperation within the USGS. A SharePoint was set up, which is a mechanism by which people can communicate with each other quickly. Portable instruments were put out, Iris Flex instruments, National Straw Motion Program of the USGS put out instruments, NEIC put some of their portables out, universities put their instruments out, such as Virginia Tech, University of Memphis, and Lamont Doherty Earth Observatory at Columbia University. Of those particular instruments, many of those were telemetered back in real time, and the data were available in real time. The blue triangles are one of the special experiments put out by Larry Brown with the assistance of Martin Chapman and of others using the Texan instruments, and they recorded some interesting aftershocks very quickly along that very dense array. Next one. This is just an example from Martin Chapman of just what one might see going out in that 70-kilometer spread as far as what the waveforms are. There's a lot of information in there. Specifically about the attenuation of the P wave and the S wave as a function of distance. Next slide. So where are the challenges? We've done great, but this is not the answer to the problems in the East. We've got challenges with respect to ground motion, determination of source parameters, earth structure, and preservation of knowledge for the future. Next one, Randy. Ground motion, these are just broadband recordings from the Virginia earthquake as a function of distance. The important thing to notice is the lack of data at short distance. It's the lack of data at short distance that really is of concern to the engineers because they only care legitimately about ground motions at short distance, and we really don't have the basis to constrain ground motion at short distance with this particular data set. Next one. Another interesting case that happened recently is an earthquake this past May in northeastern Texas. This is just the shake map image that's produced by the U.S. Geological Survey. The little dots and the arrow bars in the bottom are the intensities from the Did You Feel It map. It's not the shake map, I apologize. The red line was posted on the website. That is the predicted amplitude versus distance relationship for that size earthquake in eastern North America. There was a huge discrepancy, and so what I did is I obtained the formula for the California relationship of amplitude versus distance, which is the blue one. And so the conclusion is that you don't want to use the current eastern North America model for attenuation of ground motion right in the Gulf Coast. Next one, please. What about source parameters? Can we actually locate earthquakes well? And some people would say yes, and other people will say no. So, and because everything depends upon station corrections, if the network is not perfect, we still need a lot of work in calibration or locations in the East. Next one, please. Just as a quick example of locations, I'm going to compare some synthetics to an observed recording. One is a simple layer cake model, the red one, and another one, the blue one, with a gradient for the MOHO is the second model, and we'll come back to that one later. Next one. This was an earthquake that occurred in June of 2011. It was a strike slip earthquake. I put the moment tensor, wanted the thing down at 27 kilometers, and someone said, well, it can't be that deep because it's a strike slip earthquake. On these particular slides, the simple models on the left we're looking at lined up with a P wave arrival as a function of source depth. The MOHO gradient model is there. Everything's in true amplitude, which says, hey, if the earthquake were shallow, you get a big surface wave. If it's deep, you're not going to get a surface wave. Next slide. Focusing on the observed traces there at St. Louis, which is about 80 kilometers away, we're looking at filtered ground velocity up to about a frequency of 1 hertz, and there are a number of features there. There's a P, here's a little bump which represents an S wave going up to the surface, refracted as P wave. The time difference is a direct indicator of depth. Another thing here is that this is a MOHO reflection of the S wave from the layer cake model. With the gradient model, it's lacking. So the data basically say that the gradient MOHO fits the data better than the little simple layer cake MOHO. The important thing is we could, with optimal earthquakes, which are not very often, the right distance, the right depth, we can get a very precise depth for the earthquake that could be used in calibration of location and other things. Next one. Okay, do we know our structure? And I'm going to look at 3 examples of items, TA array up in North Dakota, in Missouri, and then the Gulf Coast. Next one, Randy. Everybody's using receiver functions. Everybody acknowledges that receiver functions have problems when you have thin sediments. Typically in the IRIS web page, you can get these with this filter setting. I prefer to calculate at a lower frequency, and I started calculating at a higher frequency. The important thing is that here are some sites in North Dakota in the Red River Valley that just ring like everything as soon as you get over to Minnesota, where the glaciers have removed everything except the mosquitoes. It's very simple. Next slide. What's happening in North Dakota? All that ringing is just caused by 30 meters of Lake Agassiz sediment sitting on top of 30 meters of glacial gravels sitting on top of Precambrian. It just obliterates any signature of the crust. Next one. This is another example of synthetics, of course, which goes back to if we derive an Earth model, it has to be validated somehow using independent data. Earthquake in 1990 recorded at Cathedral Cave and Iris Station. The rest are synthetics. Of the models here, 3 of the models are from a joint inversion of receiver functions and surface wave dispersion. All those models happen to have a gradient, which is what the data demanded. What the gradient gives is this very high frequency, sharp S-wave arrival. And to me, that's a validation, whereas the layer cake model does not have that sharp S-wave arrival. It's a validation that the MOHO gradient there, the MOHO is a gradient there as opposed to a little sharp layer cake. Next one, please. Dispersion observations, group velocities from cross correlation of ground noise from earthquake data. For Rayleigh waves on the right, Love waves on the left. Don't forget about that. That's just data. The blue line would be a reference model that I used for modeling earthquakes. That was a simple layer cake model in that I used in the eastern U.S. This is one I would use in the Gulf Coast or in the western U.S. Very nice pattern. Let's look at the next slide. This is the group velocities measured down near the Gulf Coast, and this is a site just right near New Orleans. And I want you to see the group velocities and how much lower they are than either of those 2 models. I have no idea what the shear wave velocities are shorter periods. It's really saying that the upper 10 kilometers there is very different than anything else in the continent, and that in turn reflects back to if you have significant events there, what velocity model to use to analyze those events in the Gulf Coast. Next one, Randy. So, where do I think we should go in the future? We should set some objectives, perhaps some suggestions are we've got to make an effort to document significant earthquakes and document that in the future so that we can solve today's problems and people 20 years from now can solve their problems. We need to improve ground motion scaling. We need to characterize the seismogenic crust because the crust is where the earthquakes occur and we need the properties of the crust in order to do the first 2. Next one. A strategy might be really to have focus on real-time monitoring and posting of results. I would also suggest we need some preemptive monitoring that we saturate some areas where we may expect to get an earthquake in the future. We need the rapid deployment. We need deployment. We need a way of getting data out there, and as data comes in, the web page and all the results are updated so we can have locations, we can have moment tensors, but people could also be doing joint hypocenter inversion and updating that periodically. We got to preserve everything and all the processing steps for the future. The next slide, it's got to be preserved. It's got to be available. We've got to build an audit trail. We also need access to various products. We need to be able to access crustal models quickly for local investigations just by going to a website and saying, give me the the best estimate today at this particular point. Next one, Randy, just quickly, where might I think on the basis of earthquakes? These are my moment tensors, which means, therefore, these things are bigger than 3.5. For some reason, they're popping off there. If we were to go back and locate those carefully, and if they really locate into a very tight geographical area, then that would be a reasonable target that after about a year or so we'll have something significant. And finally, the last one here is a personal thing. We've got to get beyond treating earthquakes as proprietary data. I think there are needs in society that require almost instantaneous analysis of these sequences. Thank you.
Well, there we go. Thank you, Bob, for that invited talk. And let's see if we have time for a question or two from the audience. Yes.
Sir?
Very interesting. I'm interested about the MOHO gradients. Some of the models have gradients above MOHO, below MOHO, some right through the MOHO. Can you comment on what kind of diagnostic in terms of figuring out which is
what I showed you there is what the data actually created, because I start with no preconception. I have no idea what the MOHO is. I know the only place that I've actually seen a sharp MOHO would be receiver functions in Korea, and then there was a poster yesterday on some receiver functions in the Shield of Saudi Arabia. That's an interesting research area, but we need that detail to understand the dynamics of the wave field.
Okay, thank you very much. We will need to move on. Our second talk is also an invited talk that Frank Vernon will present on the behalf of his many co-authors, Mid-continental Seismicity in the U.S. as recorded by the USArray. Let's go to the first slide. There we go. And we can actually go play.
Yeah, I guess I'm the first keynote person of the session. All right, thank you for inviting me and my group to participate in this session. I'm here representing the USArray program and the Array Network facility at UCSD, which does a lot of processing on the TA data on a daily basis. So, next slide. So just a quick overview of what USArray is. In the transportable array, we have a laser right here somewhere. There we go. Okay. So we have a standard TA vault with a broadband seismometer located in the bottom, data acquisition system with 40 samples per second and 1 sample per second data, co-located with an infrasound acquisition system, which was talked about earlier today in various sessions, and then everything's telemetered in real time back to San Diego and onto the IRIS DMC. The one thing that is kind of unique about this particular experiment is that we're laying things out on a 70-kilometer even grid, and we have basically essentially the same transfer function instrument response across the whole network. So we're getting a view of the U.S. in a common way, except for a very short period of time when we're locating each station. Kind of the next one. So this is a map of how the array progresses. We started in the west. We migrate off to the east. Each red station is a USArray station. The other color stations are contributed from other networks. And you can see this is over a 7-year period to this point in time, and that's we sort of get a drive-by view of the seismicity. We get each station, individual stations in place for about 2 years, but each day we basically pick up one station on the back end and move it up on the front end for every working day of the year. So we don't, the legacy is going to be the view of the snapshot that we get for that particular time. Next. One of the primary goals of our observations is to get teleseismic seismicity to image for, which is used for imaging structure and so forth. You can see this is the catalog that we've acquired of magnitude 5 or greater earthquakes worldwide. We've pretty much highlight every plate boundary that you can see, plus a lot of other seismicity from other interesting places. But for this purpose of this talk, next slide. We're actually looking at what we're observing in the mid-continent and the seismicity in the regions which haven't been so well covered before. And so, right as of today, we have 433 active stations plus 132 contributing stations. We've decommissioned 985 stations, and we have 49 stations which are also decommissioned from the contributed network, and 44 stations have been adopted. And I was going to emphasize what Bob was saying, is that there is a proposal that once we finish rolling off to the end of the East Coast, that there's a proposal in the works to try and leave a legacy of about order 200 stations in this region from about here out to the East Coast, and that would, I think, greatly help the long-term monitoring objectives of the East Coast. Next. So basically what the real-time workflow is, we collect data from the station real-time. We collect all external catalogs that we can find from the authoritative regional networks. We run a real-time detection algorithm to find the arrivals, associate with an association with the detections is made to locate and associate with events, and we build daily reports with the origins and the events, and then those are, have also data availability and data gaps. All the waveform data and all the origins and all the picks and all the detections are available and have been used by others also. Next. So we have an analyst review come in afterwards. They refine the automatic picks and add missing picks. In the U.S. events, the process is that we locate the events within the array footprint. We associate with the regional bulletins. We catalog. We calculate local magnitudes and attach authoritative information. So if there's a regional network and local involved there, we will attach them as authoritative, and we would be a secondary author of an origin. Next. And so here's the basic authoritative regions that we've been working with. These are very similar to what the ANSS has now derived to. We've actually started building these even before some of the later ANSS authoritative regions have been put together. But you can see which part of the regions to which we defer to the local catalogs, but you also see large parts of the country where there is nobody there. Next. So we have 50,000 preferred origins in the bulletin from April 2004 through June 2012. The authoritative author is shown by the color, like up in here, the blue ones are Berkeley, the red ones are us, and various other colors in various regions. It's a little hard to see, but you can get an idea of the snapshot of the seismicity that we have seen during the course of this experiment and observations. Next. So one thing that we're very curious about is to see what are we observing that is not produced in another catalog. It's not in the Berkeley catalog, not in the Caltech catalog, not in NEIC's catalog, anybody else who's running a standard seismic network inside the U.S. So you can see when we were in the first few years we're on the West Coast, we found about 4% of the events that in that catalog that were not identified in other catalogs at that time. And as we start moving further and further east, we start getting those numbers start rising. We start seeing that a third of the events start getting up in here. 50% of the events start as we move out further. Next. And getting all the way up into the 80% when you get in this part of the world, and dropping back to 70 as we get, and dropping back further and further as we get into more instrumented areas on the East Coast. But this gives you an idea of giving us a constant coverage of what the standard set of instruments in basically a 10-station association for most of the network, particularly in the West, and then we dropped it down to a 7-station association as we went further east. Next. So one of the things that we wanted to look at is like how much of this, as we move further and further east, in each part of the country, is how much of the data we're seeing is actually might be attributed to anthropogenic effects. So looking on the Pacific region, we can see that we have in the weekdays we have the dark blue and the weekends we have purple, and we see that there's a spike of activity during the normal workout, and this is in the local hour, not in UTC. So we're trying to see what times actually normal working hours of mines and things like that. And you see that on the weekdays that there's a spike in activity, and from the 2 o'clock to 4 o'clock in the afternoon. And basically it's flat rate of seismicity on the weekends all day long. Next. When we start looking further and further east in the mountain time zone, we see this huge dominance of activity in here. So we have a little bit of activity in the background at night on either side, but on the weekends or on the weekdays, we're just a preponderance of this. And also in the same thing in the central eastern U.S. Now, one of the things our catalog that we do not make a discrimination of anthropogenic events versus natural events. We're trying to catalog all activity that shakes the ground, and so it's not within our scope or within the ability of our resources to actually go back and partition those out. Next. So looking at the Pacific time zone, you can see a comparison of the overall and the weekend activity. You can see that the weekend activity is a constant rate. Nothing really changes there. Next. But then you see the same thing at nighttime for the mountain time zone and for the central and eastern time zone. So we see a fairly constant rate of seismicity for both in hours where there's not a lot of human activity. Next. So during the local daytime, you can see that here's the catalogs partitioning the whole U.S. that we've done so far through June. This particular map goes through June of 2012. And you see that the activity is fairly characteristic in the west and the Intermountain West, and a fair amount of activity in other places. Next. But here you notice that we look at the same event on the nighttime, same map in the nighttime, we have half as number of events. I need to go backwards. Was this keyboard? Yeah. Okay, so you'll notice that this set of events in British Columbia do not exist at night. So we've clearly got major activity going on up here that are mining activity. Same thing here in Wyoming. Whoops, too far. Sorry about that. And then you find other places in the further down into the parts of the southern U.S. where we have the same type of thing. Next, go. And then in the bulletin that we've, since from moving to June to October, you'll also see that we're starting to see a lot more events out in this particular region as the USArray footprint starts rolling into this particular part of the U.S. Next. So looking in more detail, these are going to be some of the same events that Bob showed you, but this is some of the types of things that we were able to isolate. This is a sequence of events in Oklahoma with a maximum 5.6 MW, and we were able to identify a large number of events in this particular region. Next. And then we can get on a much higher resolution into detailed studies of this, and I know people have gone actually far more into research on this because various groups have used these data, their own local data, and their aftershock data, like Bob was talking about, to come into much higher refined structures. These are only events. These are only events that we were located using the TA stations alone. Next. In Arkansas, similar thing. We have the 4.7 in eastern Arkansas, and then we have a 3.9 in Kentucky. Next. And then, doesn't look that dissimilar from what Bob was showing earlier about the Arkansas earthquake. So we're having fairly consistent views of the data itself. Next. And in the big state of Texas, where one of my sponsors is from on this talk, we have, or used to be from, I should say, we have a set of events. We have a 3.7, a 4.8, a 4.3, and a 4.8 during the period of that USArray has operated in here, and they've basically two events down in this southern Texas, one out in eastern, and one up in central. And so this gives you an idea of the seismicity there. If you go to the next motion, you can see most of these events have actually are earthquakes that are not around activity of known mining activity. We've done a fairly complete compilation of all available mine locations, and in this case, there's not much activity with the possibility of this area right here. So whether there's a causality or not, it's not easy to say. Next. And then in the eastern U.S., you see we're starting to move into here. We have the Virginia earthquake, as we talked about before. We have an earthquake up here in New York, 4.0 earlier in the year. And then we have, various sets of seismicity that are starting to fill in as the footprint, which is now up to about right here in place. Next. But as you can see, that a large amount of this is going to be clearly dominated by the mining activity in this region right here. So we have by starting to look at the catalog regions where we're able to find events in our bulletins, and then looking at where the seismicity is occurring compared to the major mining areas, we're seeing that most of this our catalog will start to be dominated by the mining and quarries. Next. So from the observations, by virtue of the grid pattern of the TA, we're getting a consistent view of the seismicity across the U.S. as the USArray rolls. We basically have a consistent view of the same gain, same sensors, same spacing across the U.S. In areas where there's been previously sparse coverage, we have observed much more seismicity than was observed before. Our magnitude complete in this level is down to order magnitude 2.0. We do not attempt to segregate anthropogenic activity from the earthquakes, and say also echoing what Bob Herman was saying earlier, we fully advocate the open data in real time with the waveforms, locations on arrivals and detections, and any other data products that can be made from these data sets. Thank you.
Thank you, Frank. Let's see if there's, we have time for a question or two. One over here. Yeah.
That I don't know the answer to. I'd have to look in the catalogs to figure that one out. I just don't know that off the top of my head. I'm sorry. We can tell you, though.
Okay, thank you very much, Frank. We'll now move along to our third talk. This is to be presented by Heather DeShone, integrating USArray and Cooperative New Madrid seismic network data to establish central U.S. catalog location magnitude and magnitude sensitivities.
Okay. Well, you read my original title. My new title does not have the word magnitude in it because I apologize. I didn't have a chance to do the magnitude sensitivity calculations. So I'm going to look at how adding the transportable array phase data makes a difference in catalog locations in the region the region that SERI is in charge of locating earthquakes in. So the New Madrid seismic zone, north of the New Madrid seismic zone outside of the Mississippi embayment, generally we'll be looking at how transportable array data changes our view of earthquake locations inside the northern Mississippi embayment and also to the north here. Next. So this work was motivated in part when I made a map a few years ago. This on the left is the Central Mississippi Valley seismic network and the Marzin seismic network circa 1987. So these were mostly vertical component seismometers. They were distributed to record New Madrid seismic zone seismicity, and there were quite a number of stations located outside the Mississippi embayment. So on my maps, this represents the Mississippi embayment. Now on the right is a picture of the current network, the Cooperative New Madrid Seismic Network, also part of the ANSS program. So this is a mix of broadband stations noted by the hexagons and short period stations. These are all three component. There are also some strong motion stations on this map. Next. Now, if you actually take the SERI catalog, so if you go to the Center for Earthquake Research and Information website and you download the catalog going back to 1974 in this region, and you actually break it when the network was reorganized in 1995, this is the picture of seismicity that you see. So there were fewer stations back then in the New Madrid seismic zone. Seismicity seems more diffuse. We now have a nice sharp picture of the New Madrid seismic zone faults. But I want to draw your attention to the seismicity outside the Mississippi embayment. This is 20 years of data. This is more than 20 years of data. And there seems to be a lot more activity outside of here. So, next. With the transportable array moving through this region, we had stations now at 70 kilometers spacing that significantly increased our station distribution in this area. Next. So the goal of this study is to understand if differences in seismicity pattern between the Central Missouri Valley catalog, so that's what I'm calling that catalog from 1974 to 1994, and the Cooperative New Madrid Seismic Network catalog, so 1995 to the present. These are a function of station distribution. If losing those stations north of the Mississippi embayment really changed our view of seismicity rate north of the embayment. We're also going to document earthquake location sensitivity to station distribution. So we're going to do jackknife testing to see what stations are most important in that area. And finally, we're going to assess how future changes in processing at SERI are going to affect catalog locations in the New Madrid seismic zone and the surrounding areas. So SERI is about to move to AQMS processing, which is going to actually change the way the earthquake locations are made. They're currently made in hypoellipse, and most of the locations I'll show today are actually done in hypoellipse. They will be moving to using hypoinverse. So my last slide is just going to show you what would happen when we just switch from hypoellipse to hypoinverse. And Mitch Withers has been kind enough to provide all the parameters that he's tuning so that change is not so great. Next. So I'm looking at a combined data set from 7/1/2011 until 10/31/2012. On the left are the stations that I'm looking at. The red stations are the Transportable Array. The green stations are the Cooperative New Madrid Seismic Network. And the blue stations are the IRIS stations in this area, or those that get reported to the DMC as IU network stations. On the right are the earthquake catalogs. Now, Frank was just saying that the Array National Facility does, in fact, create their own catalog. They use transportable array stations, and they pick up IU network stations when they make their catalog in this region. Now, the SERI uses the Cooperative New Madrid Seismic Zone stations, and they also pick up the IU stations. And for special earthquakes, they have been picking up transportable array stations. So we're going to try to tease out how all of these phases change earthquake locations in this area. Next. All right. So SERI uses 4 velocity models in this region. When they're recording, this is the New Madrid Seismic Zone. So when they're recording inside the New Madrid Seismic Zone, they use a velocity model called the Panda model, which includes a low velocity zone, and that's shown here in red. To the south of New Madrid, or what I call the southern embayment or the greater embayment, they use a model that does not contain this low velocity zone. They have a separate model for Arkansas, which they named the Enola model for historic reasons. And then outside, they call this the Uplands model, but this will essentially be the model I use for all earthquake locations outside of the Mississippi embayment. Next. Now, I've tried to keep everything except the distribution of phases the same in this case. So what I'm going to show here is just kind of a work through for 2 good-sized earthquakes, a magnitude 3.9 and a magnitude 2.5 that were located on the northern arm of the New Madrid Seismic Zone. In green are the map view and depth distributions of these 2 earthquakes if you went to the SERI website and just downloaded the earthquake locations. In red are the locations for the same 2 events if you pulled them out of the Array National Facilities catalog. Now, if you just combine those 2 phases, the SERI catalog and the ANF phases, and relocated, next, you'd get the earthquake locations shown here in blue. And as part of a USGS project, I was also charged with picking transportable array data as the TA moved through the central US. So essentially we have the SERI phases and then those phases picked by the Array National Facility, but we also have kind of the same thing. We have the SERI phases and phases picked on the transportable array by undergraduates at the University of Memphis and myself over the last year, so I just call those the SMU phases. Right? So if you just combine SERI and ANF, you get the blue locations. If you combine SERI with all of the phases my undergraduates and I have picked, you get the pink locations. Now, for these 2 events, SERI actually picked up a number of transportable array stations in part of their catalog. So if you remove those, so this is, if these earthquakes had happened 2 years ago and the transportable array wasn't there, what would these locations be in the catalog? This is what you would get next, the orange, all right? So one thing that might become apparent is it's generally thought that the SERI earthquake locations are good to about 1 kilometer, but you'll notice that the depths for these 2 good-sized events vary considerably based on whether or not you're picking up Array National Facility data or this data located mostly outside the Mississippi embayment. And in fact, most of the time that actually leads to a shallowing of the earthquake location. Next. All right, so tables. My talk is full of tables. I'll try to draw your attention to the important points. So here I'm looking at just those earthquakes in the New Madrid Seismic Zone located inside that Panda velocity model. SERI minus CNMSN represents the current SERI catalog minus the TA, okay? So when SERI picked up TA stations, they picked up TA stations for 39 events over the last year, basically. So I removed those transportable events just to get a feel for, okay, well, what was the difference? What would the Siri catalog have looked like for those 39 events? And the mean latitude, longitude, and depth changes are near zero, and the standard deviations on those are within the uncertainty estimates of the catalog locations, 1 kilometer. Now, if you take the Siri catalog locations and you subtract out for the 22 events in common between Siri and ANF in this area, so you difference those locations, you'll see mean changes that, half a kilometer, but in depth, almost 2 kilometers with a depth standard deviation of nearly 3. And you can do that same thing. So Siri plus SMU would be the SMU picks of the transportable array. Now, in this case, there's 171 earthquakes, and this is because my undergraduates were told to pick everything, all right? And so they actually picked 171 transportable array picks, and that drives that down a little, standard deviation 1.6. I need to go faster. All right, and this is the same thing for south of the New Madrid seismic zone. The numbers go up a little bit. Dwell on that. All right, so upland seismicity rate. Now, I have not removed blasts. So my attempt to remove blasts was to name things aftershocks. There are clusters of seismicity in the Array National Facilities catalog that I think are likely anthropogenic. And so what I did is essentially identify aftershock areas and removed them to do this rate calculation. So what I'm saying here is that the Array National Facility, or the use of the transportable array data, has created 1.6, maybe a little higher, more earthquakes in the catalog than just using the current network would do. So I'll just keep going. Doing the same location sensitivity test with the uplands data, Siri tends to pick more transportable array data for events outside the Mississippi embayment because those data don't usually exist. It should give them higher quality earthquake locations. I just want to point out that the mean change this leads to, if like Siri versus what it would have been 2 years ago, almost a kilometer difference in depth with a huge standard deviation, almost 10 kilometer depth difference. If you take the 18 events that occur in both the Siri and the Array National Facilities catalog and just difference them, I want to draw your attention to that the mean depth difference is 3 kilometers with a standard deviation of nearly 10 kilometers. If you combine the Siri and Array National Facility data, again, you see this mean change of 3 kilometers with a large standard deviation. Next. The jackknife testing shows which stations are most important. So in this case, I drop one station out at a time. I remove duplicates, so I prefer Siri phase data over Array National Facility and Array National Facility over SMU picks. And I'm only looking at events outside the Mississippi embayment. The stations in bold are those that have a mean change in standard deviations of greater than a kilometer. We'll look at those in map view next. So those important stations are marked by the stars. Here are just the uplands events. These are scaled by number of arrivals, so you can get a feel for which one was probably a bigger earthquake. So I think adding data in this area is pretty important. And then finally, if you look at what's going to happen in the future when Siri moves from hypoellipse to hypoinverse, within the New Madrid seismic zone, it's tuned pretty well. The mean change in latitude, longitude, and depth is almost zero. The standard deviations are within known errors. But in the greater embayment area and in the uplands area, the standard deviations get pretty high. Notice the uplands are outside the embayment, standard deviation of nearly 7. So there's either some tuning that needs to still be done with the hypoinverse parameterization before it goes into effect, or should really keep this in mind. So in conclusion, the addition of select TA stations are going to increase earthquake detection rates outside the embayment. I saw about 1.6 times more large events outside the embayment using ANF data. If you just didn't consider whether or not those were blasts or not, that would be 9.6 more events in the ANF catalog. The inclusions of phases at stations outside the embayment have a significant effect on earthquake depth. The mean depth changes are 1 to 3 kilometers with standard deviations of up to 10. And again, the epicentral changes associated with this change from hypoellipse to hypoinverse are going to be within expected uncertainties, but there are going to be significant deviations in depth, again, in the uplands area or in the southern embayment area. All right, so I need to thank Mitch Withers and his crew at Siri and Frank Vernon and Luciana Estes who've been giving me Array National Facility data and the USGS. Thanks.
Thank you, Heather. Do we have a question? Well, let me ask one. That in Bob Herman's talk, he made the point that there are wide differences in the waveforms looking at shallow versus deep events. Have you given thought to whether we should be using more waveform type discrimination, particularly for identifying blasts and other sources?
Yes, I've been thinking about blasts here at AGU, and I was going to go back and do a little more careful look at the waveforms to try to discriminate, but everyone that's ever done it tells me that it's a very time-consuming process, so I don't know how you do it automatically.
Okay, thank you. So we're going to move on now to our third invited talk. This will be by Austin Holland, Insights into Oklahoma's Increased Seismicity, aided by the incorporation of the Transportable Array in regional earthquake monitoring. Austin.
Thank you. Next slide. So I've spent a lot of time over the last year working on the Oklahoma catalog. I got to Oklahoma in the beginning of 2010, and so I've been working a lot at cleaning that catalog up and becoming familiar with it. And one of the things I had to evaluate as the TA came through was our magnitude of completeness over time. I'm fairly convinced through several different methods that I am complete to, or the Oklahoma Geological Survey catalog is complete to a magnitude 2.9 back to 1980 at least. And below that, it gets a little more tricky to discern the magnitude of completeness. I'll show a slide later that addresses that a little more. I just wanted you to be aware of the many different things I'm doing with the catalog, but certainly if you have questions later, don't hesitate to ask. Next slide. So this shows the declustered catalog for Oklahoma from 1882 to 2011. Most of the seismicity is concentrated within the central portion of the state and generally is close to, but not directly on, some of the major faults located within Oklahoma. The major faults are shown as the thick black lines on the slide. And the earthquake magnitudes are clustered, or the earthquake symbols are scaled by magnitude. The largest earthquakes that occur in Oklahoma are the magnitude 5.5 that occurred in 1952 here, and then the magnitude 5.7 that occurred last year there in Prague. Next slide. So as we've heard before, the Transportable Array has been moving across the country. It moved into Oklahoma in 2009, and the last stations moved out in 2012. It was a sad day because they did a lot for our ability to know a lot about the seismicity, and that will be the focus of the rest of the talk, is how those stations have dramatically improved our understanding and then some of the insights from the seismicity that has occurred. Next slide. So we have seen a dramatic seismicity increase in Oklahoma since 2009. And one of the questions I always get is, how do you know this isn't real and not an artifact of all those seismic stations that happen to come through Oklahoma at the same time? We had an additional 39 stations in the state, and they did make a real difference for us. But one way to look at that is the number of reported earthquakes, the number of felt earthquakes that were reported to the Oklahoma Geological Survey. This goes back to 1975, and you can see it's fairly consistent through time, and then we get this very large spike. And if we look at then the magnitude 3 and greater earthquakes, we see a parallel to the number of felt earthquakes within the state. So I mentioned I'd address the magnitude of completeness a little more. On the left here is the complete catalog. I've broken it into 2 time sequences, from 1980 to 2008, and then from 2009 to 2012. And so here you can see, and I've binned it in half magnitude unit bins, And here you can see the trend for 1980 to 2008 is much lower than the trend for 2009 to 2012. And we see the same thing, although a lot more scatter in the declustered catalog. This doesn't look so bad when I don't bin on a half-degree bins. But the point is, our magnitude of completeness here is, for both cases, is about a magnitude 2.2, either in the declustered catalog or in the complete catalog. Next slide. So just plotting the cumulative number of earthquakes in the Oklahoma catalog from 1882 to present, we can see as we go forward, we don't have a whole lot of earthquakes until we started having more population within the state of Oklahoma. The first seismic station in Oklahoma occurred in 1962, and we had a regional network in 1978 that has operated continuously since then. And you can see that there are some regions within Oklahoma that have had historical seismicity at fairly continuous rates. Until about 2000, we may see some acceleration in some of these regions. An important point to note is that our lowest areas of seismicity are in the western portions of Oklahoma here, and they do not see a rate increase. These two lines that are reaching for the sky, these are the two centrally located boxes here in central Oklahoma. The Prague earthquake is in the browner color, and the Jones earthquake swarm, which is occurring just outside Oklahoma City, is occurring right here in the yellow. So dramatic increases in these two regions of Oklahoma, although the rest of the regions in Oklahoma have seen an increase in the last couple of years. Next slide. So obviously, rate increases of this order of magnitude have a dramatic effect on the seismic hazard that you'd assume. So this is a uniform hazard spectra calculated from a probabilistic seismic hazard assessment for a site just outside of Oklahoma City, and using many different return periods. But this is just evaluating the period from 1882 to 2008. If we take the complete catalog from 2009 to 2011 and run the same hazard assessment, we get 4 times greater ground motion at the same return period. So a really dramatic effect on the seismic hazard. And how to properly deal with these sorts of rate changes in a seismic hazard assessment, I think, is probably an open question. Next slide. So zooming in a little, these slides have been shown a lot, but this is the Prague sequence here. The years are colored, so the green is 2012 earthquakes. This slide was generated earlier in the year. 2011 are the orange, and 2010 are the blue. That color got translated. And we can see here the transportable array stations and then regional stations within the area. We had really good coverage of regional stations within central Oklahoma, but in addition to those, the USGS provided netquake instruments to go in this area, and then some were moved over here following the magnitude 5.7 earthquake. So we have really good station coverage here, and the TA just made it incredibly better. Next slide. So looking at the focal mechanisms, we were able to calculate about 150 focal mechanisms throughout the state over about the 2.5-year period that the transportable array was in the state of Oklahoma. These are from regional stations and incorporating in the transportable array. And this is for the Prague sequence, the major fault plane of the main shock, the magnitude 5.7 is shown here. And you can see there is some scatter. These are the p-axes, and shown as circles, and inverted triangles are the t-axes. So there are some scatter in the p and t-axes, but primarily it's all the seismicities occurring on this fault plane here. We would not have been able to calculate this many regional focal mechanisms if we had not had the TA available within the state. Next slide. So we also have done the focal mechanisms for the Jones swarm, but I just wanted to talk a little bit about the Jones swarm. It's averaging about 2 earthquakes per day. It started in 2009 and continues today. It's a zone of diffuse seismicity. It's been broadening through time. The time progression is quite interesting. It was centrally located in Jones, which is just east of Oklahoma City. And the largest earthquake to occur in the sequence is a magnitude 4. And here is a time magnitude plot. And we don't see any significant main shock aftershock sequences. It's a true swarm that's occurring here. And if we look at the B values for the Jones sequence versus the rest of Oklahoma provides B values very close to 1, and the Jones sequence is providing a B value of about 1.3. Next slide. So if we look at the focal mechanisms for them, there's a much greater amount of scatter, and you can see here the scattered seismicity. And these inverted triangles show the location of the netquakes instruments and regional seismic stations. And one of the things I'd like to point out here is this red star. This is a oil and gas operator that is injecting water into the Arbuckle in the basement in this location. And they put out and sponsored these seismic stations for us so that we'd have a better understanding of the seismicity in the area. So these are pretty dense, and we'll look a little bit more at some data from this well and these orientations next. So this is an image log from that well I pointed out just a minute ago, just to the southeast of the heart of the Jones swarm, or southwest, I'm sorry. And what we see are 2 major orientations of open fractures. And the first is sort of this north-south orientation, and the second is this orientation here. And these are the azimuths of our possible nodal planes from focal mechanisms, and we can see that our 2 major distributions of fault plane orientations match quite well with the open fractures in the basement just a few miles to the southwest. Next slide. And so one of the things I did was take the regional seismicity and define what the optimal orientation of faults are for that regional faults or major faults in the area. And so the faults that are most favorably oriented are shown in red, less favorable in yellow, and least favorable in green. And so you can see that even along strike, many of these faults change colors. Here in the Prague, the main Wilzetta branch is this yellow, but the fault occurred, or the earthquake occurred on a fault splay off the Wilzetta fault. Next slide. So general observations, the increase in Oklahoma earthquakes has been dramatic. Adding in the transportable array has dramatically improved our data products during this time frame, and that the earthquake slip planes appear to be controlled by large pre-existing faults. Next slide. So I'm going to jump real quickly and hopefully get through all this. There is an example where we saw 85 earthquakes that were fairly well constrained. 16 of them were greater than magnitude 2. Several were felt by a local resident. And these ended up correlating quite well to an injection well that was located just 2 kilometers away. So the injection well is shown here, and the earthquakes fell on this fault plane that is parallel or subparallel to the secondary structures in the area. Next slide. So this shows the temporal correlation of number of earthquakes to injection parameters, and the time correlation is strengthened by the fact that the well was shut down during a blizzard, and so they stopped injecting, the earthquake ceased, and when they started back up again, the earthquakes started up again. Next slide. So one of the next questions is, how many more of these might we see if we look through the Oklahoma catalog? Next slide. So this is just by region where the wells have been completed since the beginning of 2010 through 2012. So these are the regions where there was a very large increase in the number of earthquakes, and you can see there haven't been very many wells completed in this area. And then in this area we had very small amount of earthquakes, and there's been a a whole lot of wells completed. Next slide. So what I did was I took a spatial and temporal filter and evaluated how many earthquakes we could possibly attribute to hydraulic fracturing within the state of Oklahoma, assuming that all completed wells were hydraulically fractured. So I just look 21 days prior to completion time and see if the earthquakes fall within this window. And I found 96 different wells that met that criteria, about 300 earthquakes. The average epicentral uncertainty was about 7 kilometers, which is partly why I picked the 8-kilometer spatial window. The maximum magnitude of these identified earthquakes was a 3.4, with 10 earthquakes having magnitudes greater than 3 or greater. This represents about 2% of all completed wells in the state during this time. Next slide. And so this is where these identified earthquakes occur throughout the state. Some are in these areas of increased seismicity, but many are in areas where we have very little seismicity. Next slide. So, of course, the next question is, well, are these meaningful? Are they coincidences? So I ran 1,000 synthetic examples of catalogs with a Poisson distributed sequence using the declustered rate of earthquakes, and I came up with anywhere from 20 to 82 wells that could be identified just through the random process of the 5,000 wells and 3,000 earthquakes occurring during this time period, and the average number is about 47 wells. So this indicates that some of these earthquakes that I identified previously could be coincidences, and some of them may be just, or may actually be triggered seismicity. Next slide. And so then the big question is how many injection wells may be triggering earthquakes. So the blue dots are injection wells within Oklahoma, and the earthquakes are shown here in pink and red. And you can see that there is some correlation between where those are. Go ahead and next slide. So I've broken it out by region again, and if we look at cumulative injection volumes through time, our greatest amount is here in this portion, and the regions which had the greatest increase in seismicity are not the areas where we've had dramatic, or we really haven't had areas of dramatic increase in injection volumes during this time frame. So there really is no obvious oil and gas connection that can appear to explain all these earthquakes we're observing. Next slide. And I think I'm out of time, so thank you very much.
Thank you, Austin. Do we have any questions? Yes.
That's the real challenge in Oklahoma is there's about 7,500 injection wells. There's not any active injection wells right in the Jones area. There are many surrounding the Jones area to both the north and the south, but there are none right in the Jones area. So those wells I showed, that image log, is further to the southwest, about 10 or 15 miles.
Okay, thank you. So our next talk is going to be presented by Daniel Sumi, Coulomb stress modeling of the 2011 magnitude 5.7 Oklahoma earthquake sequence.
Method? No. And then I can click. So you guys got to see my whole talk in reverse. Okay. Well, thank you for that intro. The Wilzetta Fault extends approximately 200 kilometers, is Pennsylvanian in age, and is not known to be active during the Quaternary. And this sequence that I'll be talking about today started with a magnitude 5.0 earthquake that occurred on November 11th, 2011, and then continued with a magnitude 5.7 foreshock less than 24 hours later on November 6th, 2011. And then also in this sequence was a magnitude 5.0 earthquake that occurred 2 days later on November 8th. 2011. And here I'm showing are the global centroid moment tensor solutions for these events. And looking at the faults here on the Wolzetta, the foreshock and the main shock both are consistent with the fault geometry. However, the aftershock seems to be occurring on an unmapped fault in this region. So here I'm showing a figure from Katie Karanen, and she has a paper that she presented on Wednesday, as well as this work is submitted currently. And so what I'm showing here in blue is the time between event A, the foreshock, and event B, the main shock earthquake. So you can see that the foreshock occurred within 200 meters and at a 1 kilometer depth away from 2 active injection wells, and that the foreshocks before the main shock event seem to be trending southwest between the foreshock and the main shock. Then in red, what I'm showing are the events between the main shock and the 5.0 aftershock, so event B and C. And then finally, you can see the aftershocks following the magnitude 5.0 earthquake shown here in green, and that a lot of these aftershocks coincide with that unmapped fault plane. Here in depth, you can see that a lot of these earthquakes occur within the Hunton limestone formation shown here in green and the Arbuckle formation. About 30% of the events located in this region, about 1.3 to 2.1 kilometers in depth. And so if you can see that a lot of these earthquakes are occurring in the shallow between 0 to 5 kilometers in depth. So what do we know from the earthquake distribution alone? Well, we know that these events define 3 near vertical fault planes that are parallel to these global centroid moment tensor solutions. That most of these events are shallow, occurring between 0 and 5 kilometers, and about 30% occurred within those sediment layers. The sequence begins near these active injection wells and then migrates southwest over time, and that there's a compelling link between the zone of injection and seismicity pattern. And this could possibly be caused by what seems to be a net fluid pressure imbalance after approximately 20 years of injection, because these 2 wells began injecting into in 1993. And one of the things that we want to look at is these poor pressure effects. And one of the ways we can look at triggering of earthquake activity is through Coulomb stress modeling. So what is the Coulomb stress modeling? So Coulomb fault failure, shown here by delta, so it's a change in the Coulomb fault failure, is related to the change in the shear stress plus an effective coefficient of friction, which has the poor pressure term wrapped up in that, as well as the change in normal stress. So we can use the Coulomb fault failure criterion to examine the aftershock distribution and to try to understand whether these regions were brought closer to failure or have a positive change in the Coulomb fault failure. Mu is the effective coefficient of friction, and here we use 0.4. It usually ranges between 0 to 0.8, but 0.4 is for strike slip or unknown faults, and this term is based primarily on work by Parson and others in 1999. The minimum stress typically found to cause changes in aftershock productivity is approximately 0.1 bar, and that work has been done by Rothstein in 1999. And so what I'll be showing in my subsequent plots is a stress bar change from -1 to 1 bar. And so hopefully that can help us illuminate whether triggering is the culprit. And then finally, I'm using the Coloumb 3.3 software to make all of my, my maps. So Coulomb stress modeling can be done in 4 major ways. One is you have specified receiver faults shown here above, where you have the shear stress change, the normal stress, and then finally the Coulomb fault failure. So you have a source fault that has the slip on it, and that slip then is received by receiver faults. And in this particular case, where you define a specified receiver fault, you assume that all the you assume that all those faults have the same geometry. The second way you can do this is look for faults that are optimally oriented for failure. And with this, you need to know something about the regional stress. And so we use the world stress map and find that there was the greatest principal stress has an azimuth of 75 degrees northeast. And you can use this, it's shown below here, for, again, shear, normal stress, and then finally Coulomb stress changes on optimally oriented slip planes. You can also do this for receiver faults with geometry that's already set. This one I don't examine at all for this particular study. And then you can also use the nodal planes from focal mechanism solutions. And I have a student, Maya Way, who was an IRIS intern over the summer with me. And she examined the first motion focal, and we were able to determine focal mechanisms using the HASH or Hardebeck and Shear software. And for this study, I'm examining the most positive stress on either nodal plane. And I should also say that faults are modeled from the empirical relations of Wells and Coppersmith in 1994. So our fault model, or area of slip, is defined using those relationships. So again, event A, this magnitude 5.0 foreshock, is modeled using that Wells and Coppersmith 1994 relationship, and it has about approximately a 3 by 3 kilometer rupture. And again, here in the blue earthquakes are the events that occur between event A foreshock and the event B main shock. And as you can see, if you look with depth, again, we're kind of constrained between 0 and 5 kilometers, and this defines a near vertical fault plane. And you can also see that most of these events are moving away from these injection wells. So just as an example, I wanted to look at the magnitude 5.0 foreshock on specified faults that are defined like itself. And this is the most easy and most familiar stress pattern to initially look at. So here above, I've plotted the shear stress change in bars, where positive changes are shown in red and negative changes are shown in blue. So these positive changes will promote failure, while the negative changes will inhibit failure. And for the shear stress change, it's positive in the direction of slip. So that slip term is, that rake is very important. And then the normal stress change, again, blue is negative, red is positive, and the positive values are representative of an unclamping of the fault, which would promote failure. And then the addition of these two terms is what you see here, which is the Coulomb fault failure. So for this magnitude 5.0 foreshock, you can see that it's inhibiting failure for specified fault types like itself. So that's an important thing to keep in mind. So we examine the change in Coulomb fault failure on a specified fault orientation now, like that of the magnitude 5.7 main shock. And we examine the maximum stress change over a 0 to 5 kilometer range, which is the depth of the aftershocks. This is based on work of Catali and Chan in 2011 that found that the depth that you calculate Coulomb fault failure on is very important, and that the best way to really be able to look at this is to examine the entire seismogenic depth range and examine the maximum term. So we follow this same methods. And as you can see, for the foreshock onto the main shock fault plane, you can see that it's plotting within this Coulomb stress change. Here I'm plotting from 0.25 to negative 0.25 bars. And you can see that this region is that the foreshock has promoted failure onto the main shock. If we examine the focal mechanisms, again derived from the HASH software, there were two events that were identified between the foreshock, shown here with the GCMT solution, the main shock's GCMT solution, and our HASH solution. And you can see that all three of these events are all red, so that means positive Coulomb stress change, or that they were promoted to failure from the foreshock. We also examined optimally oriented strike-slip faults from, again, the regional stress distribution found from the world stress map. And we see that the regional orientation of stress promotes failure on right lateral strike-slip faults following the main shock, following the foreshock, which is consistent with this distribution of right lateral aftershock activity. So the earthquakes in red are the ones between the foreshock event A and the main shock event B and the aftershock event C, and the magnitude 5.7 main shock from the Wells and Coppersmith relations is about 8 by 5 kilometer rupture, and this 8 kilometer long is consistent with the extent of the aftershocks. So we examine the Coulomb stress change on orientations that are parallel to the main shock fault plane, again averaged over the 0 to 5 kilometers depth. And you can see that on specified fault orientation such as itself, that it again promotes failure. So and that was just based from the main shock alone. If we throw the foreshock into this picture, the foreshock plus the main shock has an incredibly complex stress pattern, but also exerts a predominantly positive Coulomb stress change on this specified main shock fault type. If we look at the aftershocks that occurred on the 5.0 aftershock fault region, we again examine orientations that are parallel to this plane, again averaged over 0 to 5 kilometers depth. And you can see in regions that there are certainly areas where it's promoting failure, but particularly in this region, it seems like that would be inhibiting failure at that site. Again, that was just for the main shock, but if we throw the foreshock and the main shock into this picture, again, it's a very complicated stress pattern, but you can see that, again, it's predominantly positive Coulomb stress change. If we look at the nodal planes, just based on the main shock, there's an equal number of earthquakes that have a positive and negative stress change, but if you look at, I don't know how to go back, but I'll just keep moving forward. Oh, thank you. And then if we look at both events, you can see that twice as many earthquakes have a stress increase compared to a negative one. If we look at optimally oriented fault planes, the foreshock and the main shock seem to promote right lateral strike slip failure on the aftershocks. If we look at the events in green, and again, this aftershock was modeled by approximately a 3 kilometer rupture. If we look at the nodal planes, we were able to examine 59 focal mechanisms, and we see that 60 have positive change in the Coulomb fault failure, and 40% have negative when we just look at what would happen if it was just the aftershock alone. If it was the main shock and the aftershock, we have 42% have positive and 58% have negative. And when we look at all three together, we see that 60% have positive and 40% have negative. If we look at the optimally oriented strike slip fault planes, failure seems to be promoted. I mean, this area is quite red, which means it promotes failure on these right lateral strike slip faults, which again is consistent with the aftershock distribution. So in summary, if we look at just the aftershocks between event A and event B, this exerts a positive Coulomb stress change, so it seems that the foreshock is triggering the main shock. And the focal mechanism solutions for these events also show a positive change in Coulomb fault failure. And so also with knowledge of the regional stress direction, the distribution of aftershocks is consistent also with triggering. If we look at between event B and event C, we also see a positive change in Coulomb stress. And most of these earthquakes also plot in regions that have a positive Coulomb failure. Also, twice as many earthquakes have focal mechanism solutions that exhibit these positive Coulomb stress changes compared to the negative. And with knowledge of the regional stress direction, again, we're seeing that triggering is the case here. Finally, if we look at the foreshock, main shock, and aftershock sequence all together, an approximately even number of focal mechanisms have positive and negative changes in Coulomb stress. And the distribution of aftershocks is consistent with this triggering. So it seems, all in all, that these events have triggered one another. And one of the things that we're kind of looking for in the future is, with an increase of the change in Coulomb stress, what is the potential for triggering on adjacent faults? Could these also be reactivated? And also, since the effective coefficient of friction has pore pressure wrapped into it, how do we decouple those sort of things and start examining what role pore pressure does change in this type of methodology? So, thank you.
Okay, thank you. We have time for a question.
Yes. No, we haven't yet. I mean, for the purposes of this talk, I wanted to stick with 0.4 because I thought looking at too many would be confusing, but it certainly does play a role, and it's something we definitely plan to look further into and see what those Coulomb stress changes are. We plan to look between 0 and 0.8 at about a 0.2 interval and see how those, what changes doing that will make. Very good question.
Okay, thank you. We're now going to move on to the next talk that will be presented by Wesley Brown, the May 17th, 2012 magnitude 4.8 earthquake near Timpson, East Texas. Was it natural or was it induced?
Thank you, Bill. Well, I'm here to make a presentation on this particular event, earthquake, the May 17th 4.8 earthquake in East Texas. I noticed it received honorable mention by our first two speakers, so it's considered very important. This is an overview of the way I'll be going about the talk. I'll give you a background on the regional historical seismicity, talk a little bit about what happened, and then basically discuss the regional geology and injection wells in the area, and talk a little bit about the location analysis from seismograms, and then I'll try to conclude whether or not that we had induced or natural event. Well, the background. In looking at this map here, here is our the event in question shaded in red. It's a 4.8 magnitude earthquake, the largest earthquake the region has seen historically. Prior to this event, we had the Gladewater 1957 earthquake being the largest, and that earthquake was also associated with fluid withdrawal, because at the time the Gladewater field was the highest volume field in the Western Hemisphere, so that event was clearly linked to fluid withdrawal from the Gladewater field. Further down south, we have the 1981 center earthquake, the closest event to the event in question here. It's a magnitude 3.2 earthquake. That earthquake it's thought to be natural because it's linked to the Mount Enterprise fault zone, which runs east-west in the southern portion of the Rusk County area here. Following the earthquake, the event, we did conduct a felt report study, and by that we collected our data, the felt report data by three methods. One, we basically posted questionnaires in the local newspaper, the Nacogdoches Daily Sentinel, as well as the Timpson local newspaper. And then Michael Brunt here and myself, we visited residents in the area and just basically asked what happened and so forth. And then this data we augmented with the DY, the Did You Feel It report that was provided to us by the USGS. Now, on this map here, we're showing the events that are, the larger events are those events that we collected while we were in the field, and the smaller events that you see, some of these smaller events, symbols are those that we received from the Did You Feel It report. The W's are basically injection wells that were located in the area. The larger symbols are wells that were over 100 barrels of water per month, 100,000 barrels of water per month, and the smaller symbols are basically the ones that are below 100,000 barrels of water per month. Oops. Upon completing the surveys and putting it all together, we discovered that the largest modified Mercalli intensity readings were about 7. That was displayed on Mr. Brunt's poster this morning. We had the pre-EarthScope, the stations in the area that were pre-EarthScope, we only had one basically, which was NATX, which is still being operational now. We got quite a bit of our data from that. And then after EarthScope, we were very fortunate to receive station number 239A, which is located up here. And in 2012, we received, we got basically 341, which is located over here in Louisiana, which later on you'll see was very critical to our study because it helped us to constrain our location in a northwest-southeast direction. We were provided with three temporary netquake units by the USGS following this event, which we deployed in the area. Well, unfortunately, though, we could only deploy them where certain conditions were met, and you'll see that most of these were along the 59 Highway 59. So we were not able to have a really good coverage so that we could triangulate properly. And I'll say a little bit more on that later on. So the geometry I'm going to say right now is less than ideal. And we also went back and searched the Nacogdoches station. And on that, we found that there are a couple events that occurred prior to the one in question. In 2008, we found one event. In 2010, we found another event. And in 2011, we found 2 events. So we see that at this point, the seismicity, for some reason, is on the rise. Whether it's natural or induced, we need to basically step back and look at the fault structure in the area. Here we have Rusk County, Nacogdoches County, and Shelby County over here, where Timpson is located. And we have a series of east-west trending fault called the Mount Enterprise Fault Zone, which is a dominant structure in the general area. These red lines, again, are from the OIINK study, and it, again, is showing the Mount Enterprise Fault Zone. The magnitudes, the MMI 7 is located in the area here just south of Timpson. This map basically is showing the distribution of injection wells in East Texas. We have several, as you can see. The larger symbols are basically showing you injection wells that account for injection volumes over 100,000 barrels of water per month, and the smaller symbols that you see are those that are less than 100,000 barrels of water per month. And as you can see, here where our highest intensity area, we have injection wells that are located in that area. Again, this is a map. This red line basically shows Highway 59 that goes through Timpson and the relative location of the Nacogdoches station. If you notice, our 3 stations are basically in a line along along Highway 59. That is because in order for us to have those stations up and running, we need a couple of parameters have to be met. One, we basically need electricity. And then we also need internet service. We also need folks who are willing and to share their homes or their businesses with us, and are friendly to researchers and universities and so forth. And then finally, we also need solid foundation where we could drill a hole in the ground and bolt the instrument down, because it has to be held in place firmly. So those conditions could only be met along Highway 59. Highway 84 runs across the north up here, but we were unable to find suitable conditions there. So again, this 341 station over here in Louisiana is very critical. It's very important to us as we try to constrain our location in this direction, coupled with the 239. Along here in this direction, we're very comfortable with our location. So our velocity structure, as I think Herman explained earlier on, is it's not very well known in this area. So But there, we know that there is a thick sedimentary layer, and we have VSVP ratios 1.8 in the upper few kilometers and maybe 1.75 at regional distances. Using that, all that, we were able to see that our SP time-lapse was about 1.1 second, as we could see from this seismogram here, 1.1 second for this aftershock, which occurred on the 16th of June. This was recorded on ETX-01. So from this 1.1 second, we were able to deduce that the depth of the event is no deeper than 4 kilometers, which is around the region where you normally find injections occurring. Again, a focal mechanism from the St. Louis group, and you see our fault plane roughly going across in this direction. It could be linked to your east-west trending faults in the Mount Enterprise region. Here we have 5 mostly aftershocks with reasonable station geometry and good PS readings. We have, again, as I said before, we have error. Our systematic error in this direction could lead to 2 to 3 kilometers error in our placement. And then we have, if you also notice here, we have 2 active injection wells located close by. So with our 2 to 3 kilometer possible error, these events here could easily be moved down to where our highest intensity is, and either way, it's still within a reasonable distance of the injection well. And I must also add that in a previous study of the Barnett Shale, Frolic also showed that wherever you have 150,000 barrels of barrels of water per month being injected in the Barnett Shale, in some cases it has been linked to seismicity, and we have a similar scenario here. We don't know necessarily what is causing some areas that have high injection wells to have seismicity, and some not, and some doesn't. But hopefully in the future we'll be able to pin that down. The injection well I showed you earlier, we have one here in the north and one here in the south. These are the volumes that for the north we have injection going on between 1890 meters and 1970 meters. That's depths of injection we're talking. And this is 100,000 barrels of water per month. And basically we see here that even though this looks like a low volume well, it is a high volume injection well, because not very many wells in Texas go up to 100,000. And down here we have one that is 260 or so thousand barrels of water per month being injected. And prior to 2006 in the area, basically nothing happened. And after injection, we find that the intensity has been kicking up ever since. And basically, in conclusion, I would want to, is it natural or is it induced? Well, let's see what we found so far. The proximity to the high injection well makes us basically conclude that it could be linked. Based on other studies, similar in similar areas, we find that it's possible and it's likely that the injection wells could be causing the earthquake. The main shock for the 4.8 earthquake is the largest in the area. We didn't have any before injection began, basically. And then our focal depth of less than 4, basically, is possible to tie it back to where we have injection, because the injection we see there roughly around 2 kilometers, and we have less than 4 kilometer focal depths. With the presence of regional faults, it's possible that they are connected somehow. And down here later on we see, well, could it be natural? It could be natural, because for the same reason, we have faults. If we have faults, it's possible. And that our conclusion basically is that the evidence is implying that it is likely caused by human activity, mainly injection wells in the area. Thank you.
Thank you, Wesley. Do we have any questions? Terry.
Yes, sir. No, it's available through the Texas Railroad Commission. It's free for download. It's go to Texas Railroad Commission, and pretty much the oil companies and so forth that operate in in Texas generally has to report this information in terms of volume of water that's being injected and so forth. So it's freely available. I'm not sure. I'm not sure.
Okay, thank you.
Thank you.
We're now going to move on to the next last talk to this part of the session. It's recent seismicity in southern Illinois and southern Missouri, initial results from the EarthScope OIINK flexible array experiment, to be presented by Xiaotao Yang.
Good afternoon, everybody. Thanks a lot for still sitting here for this very important session. I will give you some encouraging results about the recent seismicity of the southern Illinois basin based on the OIINK flexible array stations. So what is the OIINK? Simply, OIINK is a sound made by pig. Of course, kidding. So where's the left key? Okay. Sorry. I think it's too fast. Okay. So EarthScope is the collaborated OIINK is the collaborated EarthScope project involving more than 120 flexible array stations across Missouri, Illinois, Indiana, and Kentucky. And this project is aiming to review the lithospheric structure beneath the Illinois basin. And this talk is just the seismicity part of the project. And we used 23 pilot OIINK stations in this study, and these stations are around the Missouri and Illinois border, and also it is a transitional boundary between the Ozark Dome in southeast Missouri and the Illinois basin. And also, we will concentrate on the two study area regions. One is the pneumatic seismic zone, which is well studied by others, and also we will concentrate on this transitional boundary between the Ozark Dome and the intercratonic Illinois basin. And our study shows that the Ozark Illinois boundary is seismically less active than the pneumatic seismic zone, which is not surprising, but this region has more deeper earthquakes than the pneumatic seismic zone does. I will show you how did I get this. And the basic structural map of the central United States shows that in the pneumatic seismic zone, there's a field rift, maybe initiated about more than 1 billion years ago, which is about late Precambrian time. And now it is still active, and while the Ozark Illinois boundary region is the transitional boundary region between the intercratonic uplift in the Ozark Dome and the intercratonic subsidence in the southern Illinois basin. So the deepest point of the Illinois basin is up to 7 kilometers deep, and we have a cross-section from the Missouri across the Ozark Dome to the southern Illinois basin, and this cross-section shows more clearly that the Precambrian basement uplift or offset between the Ozark Dome and the Illinois Basin is up to 7 kilometers depth. It is a very big valley. And we will focus especially on this transitional zone or boundary. And there are a lot of earthquakes happening in this region. Some of you may have already seen this figure several times. And most of the earthquakes concentrated in certain structural features, which is not surprising too. And in the pneumatic seismic zone, the earthquakes are concentrated along the field rift or along the pneumatic seismic zone. And in the Ozark, Illinois boundary, it is also concentrated in the transitional boundary, which is in the northwest or southeast direction. And we also combine other historical catalogs from NEIC and also from Nautilus catalog. And the first issue for data processing is to discriminate the earthquakes from the blasts. So this is the typical local earthquake waveform, and this waveform shows the clear P and an ice wave, which is with time difference of about 20 seconds. And for a typical explosion or blast, the waveform also shows some features. Like 20 seconds after the P of first arrival, we got the very obvious short period surface wave. We use this to discriminate the blasts from earthquakes. But I have to say that this method was not applied for all of the blasts or explosions. Using this method, we did a test in 20 days period, and among the 857 events, only less than 10% of them are earthquakes. That means that more than 90% are blasts. Among this less than 10% of earthquakes, only 2% of them are local earthquakes. So in local scale, that means 2 local earthquakes and 769 explosions or blasts. That means only less than 1% of them are local earthquakes. So as I said, like this method, no, I will talk about that later, sorry. So more than 70% of the blasts happen during the local daytime, which in UTC is about 16 to 23. As I said, that this method to distinguish the blasts are not applied for all of the blasts. So the method we use is to just discard this time period when I was doing the seismic activity analysis. Okay, this is data we acquired during the 208 days from July 29th, 2011 to February 21st, 2012. The green and dark or gray dots are the epicenters, where the green dots are the epicenters located by our OIINK network, and the gray dots are the locations got from this original network, mostly are from the Syrian network. And the triangles are seismic stations, where the yellow triangles are the OIINK stations. So after I taken the depths into account, I got a very interesting figure. That here, the colors are for different depths. Like the yellow means the depth which is about upper crust is 0 to 10. The blue means the depth is about middle upper crust, 10 to 20 kilometers. And the green, the red means the depth from 20 to 40 kilometers, which is about lower crust. And the stars are the locations got from the OIINK or located by the OIINK. And this figure shows interesting that the earthquakes in the Ozark-Illinois boundary region, concentrated at a more deeper range, which is about 10 to 20. And while the pneumatic seismic zone in here, like most of the earthquakes concentrated in the during or within the low upper crust, which is about 0 to 10. And using this in this figure, the vertical axis is the depth of the earthquakes, and the x-axis is the number of earthquakes with certain depths. This is the historical histogram. It shows more clearly that in the pneumatic seismic zone, most of the earthquakes concentrated in the within the depths of from 5 to 10, while in the Ozark-Illinois boundary, most of the earthquakes concentrated in the within the 10 to 15 kilometers. And from the historical data, it is also show the similar pattern in the pneumatic seismic zone, which is also from 5 to 10 kilometers. And but after overlaying the results from the OIINK catalog, we could see that although we got only a small data set from the OIINK observation, we have a consistent pattern in the pneumatic seismic zone, and also similar pattern in the Ozark-Illinois boundary. But I will show you later that they miss a lot of small earthquakes. And we computed the magnitudes of the earthquakes using the Antelope local magnitude calculator, and then calibrated the series calibrated to the series local magnitudes. And the number of earthquakes with certain magnitude was normalized by time and area, and also we got the logarithmic value of 2 show the seismic activities. And for the OIINK data, we excluded the blast time period, which is from 16 to 23. And this is the data we use that most of the data, or all of the data, have magnitudes greater than 1.0. And most of the small earthquakes, which is in blue dots, are located by our OIINK observations. So we got more smaller earthquakes in series catalog. And this is the very interesting figure that the horizontal axis is the magnitudes, the vertical axis is the seismic activity, which is in logarithmic value. But the axis skew is not logarithmic. So you really need to pay more attention, about the samples, because there are a lot of samples. You only need to know that this stores or data from the OIINK observation, and the blue color is for the Ozark-Illinois boundary, while the red color is for the pneumatic seismic zone. So for the Ozark-Illinois boundary region, the regional network or the series network only recorded or detected earthquakes with magnitude greater than 2, while we detected a lot of earthquakes with magnitude greater than 1.5. Like there's a 0.5 difference, because it is in for the magnitude. That means we could record 5 times more earthquakes than the regional network, and the seismic activity difference between the pneumatic seismic zone and the Ozark-Illinois boundary is about 0.8 to 1.0. That means the pneumatic seismic zone has about 10 times more earthquakes than the Ozark-Illinois boundary. It's not surprising. So let's just summarize my conclusions for the seismicity of the old Illinois boundary and the New Madrid seismic zone. And we use the short period surface wave to discriminate the blasts and the earthquakes, and we got only less than 10% of earthquakes. And the old Illinois boundary is less active than the New Madrid seismic zone. But this region has more deeper earthquakes than the Madrid seismic zone. And also we lowered the earthquake detection threshold about 0.5 to about 1.5, so we could record 5 times more earthquakes than the regional network. That's all. Thanks for your attention.
Okay, thank you. Do we have any questions? Okay, we'll move on to the final talk of this part of the session. It's to be presented by Frank Prazaclia, Evidence for Persistent Faulting Consistent with the 23 August 2011 Louisa County, Virginia earthquake.
Oh, sure.
And I think Claudio is going to be the presenter here. Yeah, okay, good.
Yes,
so Claudio,
I'm not Frank, I'm Claudio Berti.
Claudio Berti.
You can still blame Frank for whatever I'm going to say. So, well, thank you for being here at the last, well, not the last, but in the late afternoon of a beautiful Friday night, Friday. And I'll try to show you some very nice evidence for, well, that are consistent with persistent and repeated faulting that is consistent with the last earthquake and focal mechanism and fault that has been illuminated by the last earthquake in the series of the in the Virginia earthquake in 2011. Now, this is a tough crowd for a geomorphologist, so I'm not going to try to say really anything intelligent about this map. But if you just, if we just focus on the distribution of earthquake, this is compiled from, what is it here? Here we go. So this is compiled for some different catalogs from 1970 to 2011. Well, the things that definitely strike me and is that this distribution of earthquake is quite puzzling and actually raises questions about whether the seismicity on the East Coast is focused on legacy structure, whether the distribution of the earthquake is actually repeating on some structure that can be active, whether there is something that can be said about the clustering, or whether even this clustering is actually actual or is not an artifact just based from a temporal point of view or an instrumentation problem. Oops, excuse me. This last earthquake in Mineral, Virginia is no exception, and in fact, in this puzzling scenario, it is in fact one of the most widely felt earthquake in the history, at least since the USGS started monitoring. There are different ways that we can try to tackle and try to say something intelligent about seismicity in the East Coast. We can do some modeling. There is a number of seismological investigations that can be done. GPS is another way that can be done, among many others. And I will try to show you some results from a technique that uses rivers and river drainages, and there has a geomorphic marker and has a long time geodetic marker. So just allow me for 3 slides to kind of introduce you everybody and try to put this on some sort of reference. We know from, well, I guess our Geology 101 that ideally a river over the long term at its equilibrium reaches an equilibrium profile. This profile is concave upward and it is stable over a long time. Now, in case of some perturbation, let's say some far-field perturbation, in this case a base-level fall, a perturbation propagates through the network. This perturbation is typically an increase in steepness, and the result is the migration of a sort of a wave of erosion that moves upstream in the river network, leaving behind terrace deposit, and in this locus of erosion, something that we call a nick point that is usually characterized by incision in the bedrock. Another thing that we can do by studying the river profile is actually some other important things can be seen by the study of river long profile. In this graph, we see in black the river long profile. That is basically the plot of elevation versus distance from the headwater to the end of the river. And this dashed line indicates places where the river is steeper than it's supposed to be. So let's consider this spike over here. It characterizes this nick point, this break in the steepness of the river. And another set of information that we can get comes from this relationship between Ks and area and the concavity that allow us to characterize two reaches of the river. One concave, that is something that is left over in the equilibrium profile, and another part of the river downstream from the nick point that is convex, that somehow highlight places where the river is not in equilibrium anymore. Another set of information can come from the sinuosity and the shape and the geometry of the channel. Just so let's use this. This is from the clear water in the Olympic Mountains as an example. If you consider the valley long profile, so just the elevation profile, you can see that there is a bump just here, located from these black arrows. If you consider the channel long profile, that is just following where the water is actually going, you can see that this bump is completely gone. And the way that the river achieved these results is by changing its sinuosity. A low sinuosity upstream of the bump, and a higher sinuosity downstream of these disturbed surfaces. Now let's see how we can, oops, excuse me. Let's see how we can use those techniques in the area of the last earthquake in Virginia. This is the distribution of the aftershock collected by the IRIS ramp and USGS station. And just let me say that those results have been just already presented today, but just let me show that the aftershock highlights beautifully the fault plane. And if you consider the profile across the AA primus, you can see that the fault plane is very nicely highlighted. It actually reaches the surface just north and west of Yanceyville. So just keep in mind this name because it will come back again during the talk. And in fact, here it is. We project on the DEM. And if you look for a river that is perfect for an analysis of paleoseismicity, well, the South Anna River doesn't get better than that. This is the course of the South Anna River. South Anna River is part of the York Basin. And you can see that it cuts across the fault that has been illuminated by the aftershocks. So if you consider that this area has the area of the emerging, or possible, or let's say the projection of the emerging fault plane, a calculation of the sinuosity show a low sinuosity upstream of the fault and a higher, relatively higher sinuosity downstream of the fault that is consistent with a perturbation and an uplift in this area, as we saw in the previous example. Now, if you consider the long profile of the South Anna River from the headwater to the confluence with the North Anna River, you can see that there is a number of these wiggly, so if you look at this wiggly line, you can see that there is a number of spikes. Now, let's disregard everything that is downstream in here. This is related to the fault zone, and so it's a much more complicated story. But if you focus in the area of the epicenter, you can see there are at least two prominent nick points, and in the slope area plot, you can see that there is quite a complication down here that is consistent with this point. So if we remove the points that are here related to this nick point, we are left with a very nicely plot that can be easily regressed. And by the regression of this data, we can extract Ks and the concavity, and they will allow us to model the upstream part of this river. So we did that, and this is the result of this modeling following this relationship. And so ideally, before the nick point reached this area, this was the previous paleosurfaces. Now, if that's true, what we expect to see is that we should see the evidence for paleo deposit laid over this surface. And so ideally, as the nick point retreat, he left behind him some evidence for these paleosurfaces, and eventually we should find a nick point. So if we go into the map area, into the area of the earthquake, and we focus on these part north of Yanceyville, theoretically in the footwall of the projected fault that moved during the earthquake. We see that we find actually a nick point right at Murd Mill. That's why the mill was there. And we see a set of deposits that I characterize with these two sets of color, brown and green. This is some evidence from the field. This is the nick point at Bird's Mill. These are some river gravel found in this area. If we go on our ideal and theoretical profile and try to project the elevation of the deposit that we found in the field, this is what we come up. And so this is the Bird's Mill, consistent with the break in the profile that we see in the river long profile. And those are the deposit that sits perfectly over the ideal and theoretical profile. Now we also have those two higher deposits that we relate to an higher terraces, and so we module with the same relationship. We draft this profile. Fortunately and likely there is a nick point up here, and those two sets of deposits sits pretty well up there. If we move south of Yanceyville, so in whatever is supposedly to be the hanging wall of the fault, excuse me, there is a number of deposits still coded in the same colors. Those are some evidence. These are very nice strat deposits. Some gravel over here, quite clear that those are river gravel. And we would try to project those deposits in the same reference. We see that those deposits don't match at all the idealized and model profile, but actually they diverge quite dramatically. And so if we try to correlate those lines, you can see that downstream of this point, the deposits are actually completely warped, and the warping is consistent across two sets two order of terraces. So if we try to put all together, we have a series of nick points at different elevations that is consistent with alluvial deposits. We have warping of geomorphic markers, and we have the change in sinuosity across this line. Everything is consistent with the history of local uplift that can be related to the movement of a fault that is very much consistent with whatever has been illuminated by the aftershocks in the Virginia earthquake, and that testify for a long history of uplift of the footwall of this fault. Now, just let me tell you that, just let me conclude with the fact that everything like that, so those evidence are actually happening in the backyard of an area that is highly populated. These sites are very critical infrastructure, and so maybe it will be the case that in the next future, when we're trying to consider the expansion and the reassessing of our system, we should probably try to look for some evidence that, although those evidence may not be, we should try to look for this kind of evidence, even if they're not really something that we are used to. If I said something like that 2 years ago to my chair, I would have been fired. It says, well, there is no such thing like deformed terraces on the East Coast. Well, maybe there are, and maybe there is more than what we know, and so maybe this is a field that can be explored in the future for assessed risk and for managing purposes. And that's it. Thank you.
Okay, thank you. Do we have any questions? Yes, Rob.
Yes, yes. Oh, sorry. Well, yes, well, I'm aware of that DEM, and those data are actually from the 30 meters DEM, so it's not the new LiDAR data. We have that data set. I didn't process that yet. What I expect, it's not a major change. Actually, we did some tests of sensitivity in other areas to detect nick points. There is not much difference in the main nick point, so the sensitivity is actually pretty. I don't expect to see biggest difference in the location of the nick points. What I expect to see is to be able to detect better surfaces that can be interpolated and has terraces, and so having much better field actually having much better prediction for field control, and then being able to find out most and much deposits that can help me in constraining those deformation.
Okay, other questions? Actually, I had one. Can you make any ballpark estimates as to what the uplift rates would be required to be consistent with the terraces that you see?
Well, this is a good question, and this is actually something that we are working on because, of course, to make a ballpark estimate, I need to have a date on those deposits. I don't have any date. This is actually something that we are working on, and we're trying to raise some money to make some cosmogenic date. But I would expect that those deposits are in the ballpark of the 1 million years old, and so it is about 10 meters of displacement.
Okay, fine. One question back here.
Yes. Yes, I do, but what I think that is that those deformations are very, the wavelength is very short, and I don't expect to see this short wavelength on a broad scale deformation like the glacial rebound, for example.
Okay, we'll take one last question from John.
Well, thank you. It will be very interesting to look at those.
Okay, thank you. We'll reconvene at 4 o'clock for an invited talk by Gail Atkinson. And I would like to ask any of the presenters for our third talk, which is titled by Sieber, and fourth talk by Gaush, if they would please come up to the podium. Thank you.